So again, not a new idea, but just extending it through now to, we can use complex numbers and things like that as well. So the relationship between the roots of a polynomial and the coefficients, so just as a reminder, there's our standard polynomial. And we saw that it didn't matter what the degree of the polynomial was. Some of the roots, 1 at a time, will always be minus b on a. 2 at a time will always be c on a. 3 at a time minus d on a. 4 at a time e on a. And we can keep going with that pattern. And that happens in all polynomials. Then, remember we saw this one for quadratics. Alpha squared plus beta squared is alpha plus beta squared minus 2 alpha beta. That also carries through. The fraction one's another common one that they do, the reciprocal of the roots, and you create an algebraic fraction. So again, that idea would still be the same. So to generalise that one, well, the square one's easy. We can say the sum of the roots squared is equal to the sum of the roots 1 at a time squared minus 2 times the sum of the roots 2 at a time. That's a nice little pattern. The fraction one's a little bit harder to do, because if it's a quadratic, we end up with the sum of the roots 1 at a time over the product of the roots. Whereas if it's a cubic, it's the sum of the roots 2 at a time over the product of the roots. If it was a quartic, it would be sum of the roots 3 at a time over the product of the roots. So I guess there is a pattern there. I mean, the bottom of the fraction is always the product of the roots. The top is the sum of the roots 1 less than the power at a time. So let's just use this cubic. We're going to find, well, we'll start off with the standard ones because we'll probably use those in other questions. So, whoop, there we go. Oh, look at that, nice little pattern. 2, 3, 4. Then let's do the standard one. They like that one, the sum of the roots squared. So remember I just said sum of the roots 1 at a time squared minus 2 times the sum of the roots 2 at a time. Subbing in what we just found, and we get negative 2. So really still all the same sorts of ideas that we saw in 3-unit. Oh, hang on. We didn't see this one in 3-unit. Sum of the roots cubed. Okay, we could create a formula like we did with the sum of the roots squared, but there is another way of doing it. Because alpha, beta and gamma are solutions to this cubic. If we sub in alpha, it would be correct. So alpha cubed minus 2 alpha squared plus etc. If I sub in beta, it would be correct. If I sub in gamma, it would be correct. If I add them all together, I get a formula. Now, if you have a look at what that formula is, I don't really need to write down all the steps, because it's really just mimicking the polynomial if you look at it. So it was x cubed, it becomes sum of the roots cubed. It was x squared, becomes sum of the roots squared. X becomes the sum of the roots 1 at a time. We just got to be careful with the constant though, because if it's a constant, that constant's going to appear in all 3 equations, so we need to multiply the constant by whatever the power of the polynomial is, in this case 3. Then we can just sub in what we've already worked out and rearrange it to make alpha cubed the subject of the formula, substitute in, and we get our answer. So then if we said sum of the, oh, hang on a sec, oh, power of 4. But you see, I could multiply everything by alpha in that equation, and it would be true. So it's exactly the same idea. And when I add those up, again, you'll notice it mimics the equation. But the difference now is, because I'm looking for power of 4, the powers have increased by 1 in each of the terms. So where we saw x cubed in the polynomial, it's now sum of the roots to the power of 4, power is 1 bigger. Where it was x squared, becomes sum of the roots cubed, power is 1 bigger. Squared, now look at the constant though. Now I don't need to multiply it by 3. So it's only when it stays as a constant that I need to multiply by whatever the power is. So in this case, it's not staying as a constant, so I can write it as minus 4, sum of the roots 1 at a time. Again, rearrange it, substitute in. Of course, the disadvantage is if they were to ask me a really high power, say I did, I don't know, alpha to the power of 10 for some insane reason. Well, in order to do that, I'd need to know power of 9, I'd need to know power of, so I'd have to work all those out, so it'd be a lot of working out. But it's a way of finding them. Alpha plus beta, alpha plus gamma, beta plus gamma. Well, look, I could expand the whole thing out. That would work. and then group the different things together, the 2 at a times and things like that. I personally find it easier to just play with simple numbers. So what I'm saying here is, look, alpha plus beta plus gamma, that's almost the sum of the roots 1 at a time. It's the sum of the roots one at a time minus gamma. The next one is the sum of the roots 1 at a time minus beta. Why do I do that? Well, I can substitute in 2 for the sum of the roots, and I've still got to do an expansion, but there's going to be a lot less things to substitute into. So when I expand that thing all out, whoa, still a fair bit though. Group them together, and you can see, there we go. We get 8 minus 4 times sum of the roots 1 at a time, 2 at a time, minus the product subbing in. Now, I don't want you to think every answer here is 2. It seems like everything's turning out to be 2 or minus 2 here. Just a coincidence. Let's have a look at that. Well, quite an old HSC one. So we've been given a monic quartic. Now this is where it was a bit mean, I thought, because you'll notice the coefficient of x cubed is a, coefficient of x squared is b, and so when you go sum of the roots 1 at a time out of habit, you go, oh, minus b on a. But of course in this one it's not minus b on a, it's minus a on 1, so you can make that, so be a bit careful. What else have they told us? It has a root of the form ki, and k a real number, and not equal to 0, otherwise that would, well, be impossible, wouldn't it? You couldn't have a root of 0 for this one, unless d was 0, I suppose. If d was 0, you could. Okay, state y. I know you love these questions where you have to make a very simple explanation, of course. Hopefully we've got this one drummed into our heads by now. All the coefficients are real, therefore solutions appear in conjugate pairs. They've told me ki is a solution, therefore its conjugate minus ki is also a solution. So something like that. So roots appear in conjugate pairs. That's why it would be. Mind you, the important bit is specifying when the coefficients are real. If you just simply said roots appear in conjugate pairs, you probably wouldn't get the mark for that, because it's only when the coefficients are real they appear in conjugate pairs. Show that C is equal to k squared a. Not a lot to go off there. So what do we know? No, we don't know we've got any multiple roots. I suppose they've just told me about ki and minus ki. It makes sense to use those, I suppose. So I'm going to factorise, you'll notice. They've told me ki is a solution, so I know x plus ki is a factor. I know x minus ki is a factor. The other factor would be a quadratic. So I've written it as x squared plus px plus q. I've just written it as. So I expand the whole thing out and group the x's together, the x squareds together, and so on. And then I guess I can equate, it's a bit like the quadratic identities idea, but now it's a quartic identity, if you like. So from there I know p is a, q plus k squared is b, k squared p is c, and k squared q is d. Can I link any of those together that c is k squared a? I've got c is k squared p, and then over here at 1 I've got p equals a. So I can combine 1 and 3 together and we get c is k squared a. Now we're going to show that c squared plus a squared d is abc. Okay, so this time I'm looking at the second one I came up with. So q is equal to b minus k squared. I'm going to put that into the fourth one, so the other one I haven't used yet. And I'll get k squared times b minus k squared is d. I don't want k's in my answer. B's, D's, I need to get A's and C's in there. But hang on, we just proved something with k squared and AC. What was it? Hang on, let's go back. C is k squared a. Another way of saying that would be that k squared would be c divided by a. So I could eliminate all those k squares by putting in c on a. Let's see how that goes. Excellent. I've eliminated the k. I've only got a, b's, c's and d's. I should be able to manipulate this now and get what they want me to show. So let's get rid of the fraction. They haven't got any fractions. Oh yeah, so there's my reason why. So yep, because k squared was c on a. And that's probably a good thing to write down, because what we proved before was not the k-squared. No, it's probably obvious, but we didn't prove k-squared was c on a. So I've sort of rearranged what we proved, so I'll mention it there. Again, remember, you have to assume whoever's marking your solution is what I call an intelligent idiot. Okay? So they know everything, they just don't know how to apply it. So they need you to help them a bit. And they'll go, oh, hang on, how did you go from here to here? Oh, that's right. Oh, okay, that makes sense. So explain yourself as you go along. All right, where are we at? Oh, yes, I've just got to move the c squared, and we should have it, shouldn't we? So there it is. Okay, so we've got that one. If 2 is also a root of the equation, so we now know 3 of the roots. There's ki minus ki and 2. And they've also told us b is equal to 0. C therefore has to be an even number. An even number. Okay, well, I don't know what that fourth solution is, so I'll call it alpha. So my roots now, remember, are alpha minus ki plus ki and 2. Now, as the other 3 roots are all integer multiples, and the sum of the roots is an integer, alpha must be an integer. I can't add 3 integers together with a non-integer and end up with an integer. That would be impossible. So I know alpha is going to be an integer. What have I substituted into there? So sum of the roots 2 at a time, isn't it? So sum of the roots 2 at a time was equal to b. So I chose that one because we're trying to show b is equal to 0. And if we have a look at it, because of the conjugates, there's a lot of cancelling happening there. Because you've got the minus 2 ki and the plus 2 ki, the minus alpha ki, the plus alpha ki. So yeah, we've ended up with k squared plus 2 alpha is 0. K squared is minus 2 alpha. Oh, sorry, we didn't have to prove b was equal to 0. They told us b was equal to 0. But it still makes sense why I used that one, because I'm going to substitute the 0 in. Now we're trying to show alpha we're trying to show c is even. C is even. So we now know k squared is minus 2 alpha. But hang on, c was k squared times a. So c now is minus 2 alpha times a. Hang on, alpha's an integer. A, I think they said was an integer, didn't they? So it's got a factor of 2. So I can write it as 2 times something. 2m. M has to be an integer. So yes, that would be an even number. It's divisible by 2. Alrighty. Time to play. These ones are in Patel. Patel will play with these ideas.